Okay guys, so this is a screencast on lesson 9.6, which is solving exponential equations. So we're going to start by going through some exponential equations of the style you've seen before, where you don't need a log to solve it. So this first example is perfect because you can see that the bases are the same. And when the bases are the same, we know we can equate the exponents. What I mean is, if I know that 6 to the x equals 6 to the power of 8, well, I can conclude that x equals 8. So we're going to use that same logic to solve this problem. Okay, so since we have 6 to the 2k equals 6 to the negative 2k minus 2, we can say 2k equals negative 2k minus 2. And then we're just going to solve that equation for k, so adding 2k to both sides and then dividing by 4. Okay, now in this next problem here, the problem is that our bases aren't already the same, but there is a way to make them the same. So if you might remember, anything to the power of 0 is 1. So this 1 can actually be written as 2 to the power of 0. So I'd have 2 to the power of r plus 1 equals 2 to the power of 0, which means that r plus 1 is 0. Which means r is negative 1. In the next problem, I'm going to use 5 as my base. And I know I need to use 5 because you always want to look at the smaller number. And in this case, it's 5. And I know that there's no other number that I could raise to a power and get 5. So 5 has to be that number. So that means that I have to look for powers of 5 that equal 125. So I know that 5 cubed equals 125. So I'm going to write this as 5 to the negative k minus 2 equals 5 cubed. So k minus 2 equals 3. So k equals 5. Okay, in this next section, you're going to need to use a log, and you'll see why in a second. Before that we get into that, I just want to introduce the change of base formula, which I may have already talked about, but here it is again. So we have our log base b of x, and that equals y. And in the change of base formula, what we know is that log of x over log of b equals y. Another way of writing this a little bit, well, let's leave it at that for now. So write down this formula, and I want to show you why this works. So you don't have to write this down for a second, just watch. So log base b of x equals y. If I was to write this in exponential form, it would be b to the power of y equals x. Now let's say I did something to both sides of the equation to solve, and what I'm going to do is I'm going to take the log of both sides. So log of b to the y equals log of x. Now we know that through properties of logs that we can take this exponent and put it out in front. So now it's y. Log b equals log x. And now if I want to get y alone, I would divide both sides by log b. So you can see that y equals log x over log b. So that's where the formula comes from. Basically the log of the argument over the log of the base. Okay, now let's start getting into some problems here. So in this first problem, 2 to the x equals 30. If you think about powers of 2, like 2 squared equals 4, 2 to the third power is 8, 2 to the fourth power is 16, 2 to the fifth power is 32. There's no integer value, like whole number, that we can substitute in for x so that 2 to the x equals 30. It's going to be somewhere between 16 and 32, so somewhere between 4 and 5, probably a little closer to 5. So we can't estimate. What we're going to do is we're going to use logs. So I'm going to do what I just did in that other example where I'm going to take the log of both sides. So log log of 2 to the power of x equals log 30. And then I'm going to do that neat trick where I take this exponent and put it out in front. So now it's x times the log of 2 equals the log of 30. Now to get x alone, I divide both sides by log 2. So go ahead and put that in your calculator. And you will get 4.9. So we were really close when we said it was between 4 and 5, closer to 5. So 4.9. All right, let's look at this next one here. 14 to the n equals 68. So this time I'm going to use a different approach. I could do the same thing as I did last time. I can take the log of both sides. I'm going to try an approach where I rewrite it in log form. So my log has a base of 14, the argument is 68, and my exponent is n. 14 to the power of n equals 68. Now I'm going to use the change of base formula, which says log of 68 over the log of 14 will give me n. So log 68, log 14. So 1.5988, so I'm going to say 1.6. So you can see how that way I think is a little bit easier, but it's a matter of preference. Okay, pause if you're still copying. I'm going to erase a bunch of this stuff because I need a little more room here. Okay, e to the power of n. Let's change colors here. So when we have e, the easier thing to do, we could take the log of both sides, but since we have e, we're going to take the natural log of both sides. So I'm going to have ln e to the power of n equals ln of 11. So move that n to the front. So n times ln of e equals ln of 11. Now you may remember that the ln of e is 1. And even if you didn't remember that, just following the steps, you would have divided both sides by the ln of e to get n alone. And your calculator knows it's 1, so no big deal. So ln 11. So we get 2.397, so 2.4. Okay. In this next problem, we don't have a ton of room to work with, but I'm going to put my answer up top here. We need to get this 15 alone, because the 15 is the base that has the power we're looking for. So since it's multiplication between the negative 2.9 and the 15, I'm going to divide both sides by negative 2.9. Now I know that I'm going to get a weird decimal there, so I'm not actually going to divide it out, but I will simplify those exponents. So let's look up here for a second. I'm going to go 15 to the power of r equals 82 over 2.9. Okay, now we can either take the log of both sides or rewrite as a log. Since most people prefer the taking the logs of both sides thing, I will do that. So log 15 to the power of r equals log of 82 over 2.9. And move my r down in front. So r log 15 equals log of 82 over 2.9. Okay. Now the last step is going to be to divide by log of 15. So my answer is 1.23, so 1.2. Okay, Same idea, pause it, try this one out, then play it. So I'm going to add 1 to both sides to get my 7 alone. So 7 to the power of p equals 71. This one I'm going to do with turning it into a log. So log base 7 of 71 equals p. Then I'm going to use my change of base. So log 71 over the log of 7 equals p. And you should get 2.19, so we'll call it 2.2. Okay, pause it, try the next one. All right, so we're getting 6 alone here. So dividing both sides by 3, I'm going to have 6 to the power of a minus 7 equals 32 over 3. The extra step that you see in the exponent is not going to be a big deal. So just leave it there for now. Treat it as just all one thing. Okay, let's take the log of both sides. So log of 6 to the a minus 7 equals log of 32 over 3. And pop that exponent to the front. So we have a minus 7 times log b equals, or sorry, that's log 6, equals log of 32 over 3. And then we got to divide both sides by the log of 6. Now that's going to give us a minus 7. So in order to just get a, whatever we get for an answer here on the right, we're going to have to add 7 to the whole thing. So in your calculator, you're going to go log 32 divided by 3, close your parentheses, divided by log 6, hit enter, then add 7, because you're adding it to the whole thing. So 8.3 is your answer. All right, try this one on your own, then come back. So we're going to get this 13 alone, because that's the base with our exponent, so adding 2. So 13 to the 9n equals 91. Take the log of both sides. I'm going to skip some steps here. And now I need to get my n alone. So here's my n right here. So what I'm going to do is I'm going to divide both sides by log 13. But I'm also going to eventually have to divide by 9, because that's just going to give me 9n. So I'm going to also put the 9 under here, but just be really careful to put that in parentheses in your calculator. So in your calculator, go log of 91, close parentheses, divided by, open parentheses, 9 log 13. And you're going to get 0.195. If you're feeling good about this, skip ahead to the next one. But if not, let's do one more together. So in this next one, you can divide both sides by -4. And of course, the negatives will cancel out. So, and I'm going to take a log of both sides. So log 17 to the power of p plus 5 equals log of 22 over 4. Okay, and then we put our exponent out in front, so we have p plus 5, and then log 17 equals log 22 over 4. Running out of room. Okay, got to divide both sides by the log of 17. And that will give me p plus 5. So in this one, I have to subtract 5 at the end. no space to write that, minus 5 at the end, okay? So we're going to go log 22 over 4 divided by log 17, hit enter, and then subtract 5. So we're going to get negative 4.4. Okay. If you were investing $4,000 at 5% compounded annually, how long would it take for your money to be worth 10 grand? Okay, so let's review the formula really quickly for annual compounding. So that would be A equals P times 1 plus R over N to the power of NT. Where, excuse me, where it says annually, that means our N equals 1. All right, so we are going to have 10 grand. So that's my future value. So 10,000 equals 4,000 times 1 plus 0.05 over 1 to the power of 1 times t. Okay, just like before, what I'm trying to do is to isolate my base, and it's this right here with this 1 plus 0.05 that has the exponent of t. So on both sides, I'm going to divide by 4,000, and I'm going to get 10,000 over 4,000. It's going to be a decimal, but in this case, a clean decimal, so 2.5. If I had to round and stuff, I'd probably leave it as 10 over 4, but I don't have to. And I'm going to clean this up and do 1.05 to the power of t. So now I can just take the log of both sides, or I can rewrite it as a log and use change of base, either way. So log 2.5, and I'm going to do that step at the same time of moving the exponent down, so t log to the 1.05. Now I have to get my t alone, so I'm going to divide both sides by log of 1.05. That will get t alone. So log of 2.5 divided by log of 1.05. So we get 18.78 years. Okay, $10,000 is invested at 4%. How long would it need to be invested to double given the following compounding? All right, so monthly. So that means that your N is 12. So, and if it's double, then it started at 10,000, it's going to be 20,000. 1 plus, the rate is 4%, over 12 to the power of 12t. Now, when I divide both sides by 10,000, I'm going to get 2. And 1 plus 0.04 divided by 12. Ugh, not a nice number. So I'm going to have to round that. 1.00. I'm going to try to give you nice numbers usually. Okay, now we take the log of both sides. Move the exponent down at the same time, so 12t log of 1.0033, and divide both sides by the log of 1.0033, and also divide it by 12. So this whole thing on the bottom, you have to put that in parentheses, or else your calculator is going to be really confused. So log 2 divided by parentheses 12 log 1.0033. Okay, for the sake of time, I'm going to skip the next part, and we'll do one with continuously, and then we'll do the half-life question. So, a $25,000 investment at 3%, how long until it's worth $40,000? And the key here is it's compounded continuously, so that means that I'm going to use my PERT formula. So 40,000 equals 25,000 times E, 2.71 to the power of 0.03 T. Okay, divide both sides by 40,000. I'm missing a 0 in my 40,000. Okay. Divide both sides by 25,000. And you get 1.6, which I didn't have to round. Otherwise, I'd probably leave it as a fraction to the E. And then we can do the natural log of both sides since we have E. So ln of 1.6, and I'm going to move the exponent out in front too at the same time. Now remember the ln of E is just 1, but you could divide both sides by the ln of E if you wanted to. It's just you're going to end up with the same thing as if you remembered it was 1. So we're dividing by ln of E, which is 1, and we're also dividing by 0.03. So in your calculator, ln of 1.6 divided by 0.03. So you get 15.67 years. All right, last question. A certain substance has a half-life of 2,000 years. If you start with 150 grams of the substance, how long before you only have 10 grams left? So remember our half-life formula is roughly this. Starting point times half to the power of time over half-life. So you end up with 10 grams. You start with 150. And time over 2,000 is the half-life. Okay, so this is just like before. With any other exponential problem, we're going to divide both sides by 150. So we're going to be left with a gnarly fraction. So I'm going to leave it at 1/15. That's 10 over 150, just simplified. Equals 0.5 to the power of t over 2,000. Okay, next step. Take the log of both sides. So log of 1 over 15 equals, and I'm going to move the exponent down, t over 2,000 log 0.5. Okay, now a couple things are happening to t. T is being multiplied by the log of 0.5 and it's being divided by 2,000. So I'm going to undo both of those things at the same time just for the sake of time here. So that means I have to times both sides by log of 0.5. I'm sorry, no, I don't times both sides by the log of 0.5. I divide both sides by the log of 0.5. Let's try that again. Divide by the log of 0.5, that cancels that, and times by 2,000. Because t is getting divided by 2,000, we want to times it by 2,000. So in your calculator, 2,000 log 1 divided by 15, close parentheses, divided by log 0.5. So the answer is 7,813.78. All right, hope that helped. If not, watch it again.